All right, welcome. Today we are diving deep into one of the absolute cornerstones of computer science, the binary tree. Seriously, this concept is at the heart of so many algorithms and systems we use every single day, and it's just as elegant as it is powerful. So let's get right into it. So, have you ever wondered what's really going on behind the scenes? How a database can find your record in a blink of an eye? Or how a giant file gets compressed down to save space? Or how a compiler even begins to understand the code you write? Well, believe it or not, the secret sauce for all of them is this surprisingly simple, elegant structure, the binary tree. So what is a binary tree? Well, at its core, the definition is incredibly simple. It's just a collection of what we call nodes, and there's one golden rule. Every single node can have 0, 1, or the absolute most 2 children. And we always call them the left child and the right child. That's really it. This one simple rule is what gives the binary tree all of its incredible power.
Okay, to really get a grip on how these trees work, we need to learn the language first. You gotta know the lingo, right? Think of it like learning the names of the pieces on a chessboard before you can play. So let's break down the anatomy of a tree.
You'll see these terms are actually pretty intuitive, especially if you just picture an upside-down family tree. The root is the single ancestor at the very top of everything. Every data point in the tree is just a node. A node that comes from another is its child, and the one above it is its parent. Simple enough, right? Now, the nodes at the very bottom, the ones with no children at all, we call those leaves. And pretty much any node that isn't a leaf, meaning it has at least one child, we call that an internal node.
Now, let's talk about the shape of the tree itself. The height of the entire tree is just the longest possible path you can take from the root all the way down to a leaf. The depth, on the other hand, is about a specific node. It's that node's personal distance from the root. And finally, a subtree, well, it's exactly what it sounds like. It's a mini tree that starts at any node you pick and includes everything below it. It's a tree within a tree.
Okay, so we've got the lingo down, but here's the thing you absolutely have to know. Not all binary trees are created equal. Not even close. Their specific shape and their properties have a huge, massive impact on how well they perform. So let's look at a few special types that you'll definitely see out in the wild.
All right, let's clear up a classic point of confusion, one that trips up even experienced developers. First, you have the perfect tree. Think of this as the supersymmetrical ideal. Every single level is packed to the brim with nodes. No gaps, anywhere. Then you have the complete tree, which is just a little more relaxed. All the levels are full except maybe the very last one. And that last level has to be filled up from left to right. This structure is super important for things like heaps.
And here are two more big ones. A full tree has a very simple rule. Every node must have either 0 children or exactly 2 children. No nodes with just one lonely child allowed. But maybe the most important concept for performance is the balanced tree. The whole goal here is to keep the tree from getting too tall and stringy. We want to keep the height as small as possible, which means our algorithms will run way, way faster. This is absolutely crucial. So we have this cool data structure, but how do we actually get the data out? You can't just loop through it like you would with an array. We need special algorithms to visit every single node in a specific, predictable order. And that whole process is called traversal. First up is preorder traversal. And the way to remember this one is super easy. Root, left, right. So you deal with the current node first, then you dive all the way down its left side, and only when that's totally done do you even start on the right side. This is really useful if you ever need to make a perfect copy of a tree. Next up, in-order traversal. The pattern here is left, root, right. You go all the way down the left, then visit the node itself, and then go all the way down the right. Now, the real magic of this one is that if you're working with a special kind of tree, a binary search tree, this traversal method will visit all the nodes in perfectly sorted order. It's incredibly handy. And finally, we've got post-order traversal. The pattern is left, right, root. So here, you explore both the left and right subtrees completely before you ever touch the parent node. This means the root is the very last thing you process. This is the go-to method when you need to, say, delete nodes from a tree, because you can safely get rid of the children before dealing with the parent. We've thrown the word performance around a few times, but let's actually make that real. How do we measure how efficient these tree operations are? Well, that's where something called Big O notation comes in, and it helps us understand how our code will behave as the tree gets bigger and bigger. This little cheat sheet gives us a fantastic snapshot. For most of these basic operations, the time it takes is O of n, where n is just the number of nodes. And that makes sense, right? If you want to visit every node, it's going to take time proportional to how many nodes there are. But look at the space complexity. It's O of h, where h is the height of the tree. That space is what's used by the recursion behind the scenes.
And that brings us to the single most important variable for tree performance. It's height, that little h. While the time to visit every node is always tied to n, the real-world speed and memory usage of so many algorithms comes down almost entirely to the height of the tree.
So in the best case scenario, what we're aiming for is a short, bushy, balanced tree like this one. In this case, the height is logarithmic, or O log n. What that means in plain English is that even if you double the number of nodes in the tree, the height only goes up by 1. That is incredibly efficient.
Now, let's talk about the worst case. If your tree is totally unbalanced, it just degenerates into what's basically a long, stringy linked list. We call this a skewed tree. Here, the height is O of n. It grows in a straight line with the number of nodes. This is just awful for performance and can even cause your program to crash with a Stack Overflow error because the recursion gets way too deep.
Okay, so after all this theory, let's tie it all back to the real world. Why did we just spend all this time learning the lingo, the traversal methods, the performance stuff? Well, the answer is simple, because binary trees are everywhere. And I mean everywhere. This is just a tiny sample. Compilers use them to figure out math equations. Your computer's file system? That's a giant tree. Data compression algorithms, 3D graphics, database indexes, priority queues, they are a true workhorse of computer science. So here's a pro tip, especially for anyone out there prepping for technical interviews. Precision is key. Don't just say tree. Be specific. Are you measuring height by the number of edges or nodes? Can you clearly explain the difference between a complete, a perfect, and a balanced tree? Nailing these details shows you really truly understand the topic. So we've seen that a basic binary tree is an amazing way to structure data, but searching through it is still O of n, which is no better than a plain old list. But what if we added just one more rule? An ordering rule that let the tree organize itself for lightning-fast searches. Well, that's the whole idea behind the binary search tree, and that's exactly what we'll be diving into next time. Thanks for watching.